What would happen if you fell into the Mariana Trench, nearly 11,000 meters below the ocean surface, where the pressure is more than 1,000 times that at sea level, equivalent to having dozens of heavy trucks pressing down on your body? Under such conditions, unprotected human tissue would be destroyed almost instantly. Nothing there should be able to survive, and yet life exists. Not large, not armoured, but soft, translucent, almost gelatinous. How can something so fragile withstand forces that even engineered materials struggle against? What is really happening in the Mariana Trench, and how much do we truly understand about it? Human physiology is not designed to withstand extreme hydrostatic pressure. As depth increases, pressure rises linearly, compressing gases and deforming soft tissues. At just a few hundred meters, lung volume is already significantly reduced. Beyond this, the structural integrity of organs begins to fail. Blood chemistry destabilizes, and cellular processes are disrupted. Even with advanced diving suits, protection is limited because pressure acts uniformly across every surface. Without a rigid, pressure-resistant vessel, survival becomes impossible long before reaching abyssal depths. This establishes a clear boundary. The deep ocean is not inherently lethal, but it is incompatible with unadapted biological systems like our own. Large pelagic predators such as tuna and sharks dominate the upper ocean, where pressure remains within biologically tolerable limits. Their physiology depends on strong musculature, active metabolism, and rigid structural systems that function efficiently in relatively stable conditions. However, these same traits become limitations at greater depths. Increased pressure affects buoyancy control, enzyme activity, and cellular integrity. As a result, even the most powerful marine predators are restricted to shallower zones. Their absence below certain depths marks the first biological boundary, an invisible line where size, speed, and strength no longer provide an advantage. Below approximately 200 meters, sunlight diminishes rapidly until it disappears entirely, marking the transition into the mesopelagic zone. In this environment, vision based on reflected light becomes ineffective. Instead, many organisms evolve bioluminescence, light produced through chemical reactions within their bodies. Species such as lanternfish use this ability for communication, camouflage, and predation. This shift represents more than a loss of light. It is a fundamental change in sensory ecology. Energy is no longer derived from photosynthesis, but from organic material descending from above, redefining how life functions in the deep ocean. At greater depths, morphology begins to diverge sharply from familiar marine forms. The fangtooth fish is a clear example. A relatively small body paired with disproportionately large teeth, adapted for seizing scarce prey in complete darkness. Its structure is not an anomaly, but a response to environmental pressure, low food availability, and limited encounters. Here, survival favours efficiency over aesthetics. What appears unnatural is, in fact, highly optimised. This marks the first point where human perception begins to misinterpret adaptation as something inherently abnormal or even threatening. Stygiomedusa gigantea is one of the largest known jellyfish species, with a bell diameter reaching up to 1 meter and 4 ribbon-like oral arms extending beyond 10 meters in length. Unlike most jellyfish, it lacks stinging tentacles and instead uses these broad appendages to envelop and trap prey. Observations of this species are extremely rare, fewer than 100 documented encounters over more than a century. Its size is not a product of aggression, but of environmental conditions, low predation pressure, and slow metabolic rates. In deep water, scale does not indicate dominance, but adaptation to scarcity and isolation. The giant isopod is a deep-sea crustacean closely related to terrestrial pillbugs, yet it can grow up to 50 centimeters in length. This dramatic increase in size is a clear example of deep-sea gigantism. Living on the ocean floor, it survives as a scavenger, feeding on carcasses that sink from upper layers. Its slow metabolism allows it to endure long periods without food, sometimes months or even years. Rather than active predation, its survival strategy is based on efficiency and patience, reflecting the extreme scarcity of resources in deep marine environments. The bigfin squid, belonging to the genus Magnapinna, is among the most unusual cephalopods ever observed in the deep ocean. Its defining feature is a set of extremely long, thin arms that bend sharply at near right angles, creating a posture unlike any other known squid. These appendages can extend several meters below the body, often trailing motionlessly in the water column. Documented sightings are exceptionally rare, and most observations come from deep-sea ROV footage. Its behavior remains largely unknown. Whether it actively hunts or passively collects drifting particles is still unclear, highlighting how little is understood about life at extreme depths. Deep-sea gigantism is not a universal rule, but a conditional response to environmental constraints. Low temperatures reduce metabolic demand, allowing organisms to grow larger over extended lifespans. At the same time, reduced predation pressure removes selective limits on size. However, energy availability remains minimal, so growth is slow and opportunistic. These factors combine to produce larger body forms in some species, while others remain small and highly specialized. Size, in this context, is not dominance. It is one of several possible solutions to surviving in an energy-limited ecosystem. At depths beyond 6,000 meters, pressure exceeds 1,000 atmospheres, placing the environment in a regime where most biological and mechanical systems fail. This is not simply an increase in force, but a fundamental shift in physical constraints. Molecules are compressed, membrane fluidity is altered, and protein structures risk destabilization. Any internal cavity becomes a point of collapse. Survival here requires complete elimination of air spaces and highly specialized biochemical adaptations. Under these conditions, size becomes a disadvantage. The deeper environment does not favor strength or scale. It enforces structural simplicity and molecular resilience. The Mariana snailfish is one of the deepest living vertebrates ever recorded, found at depths exceeding 8,000 meters. Its body appears fragile, translucent, scaleless, and gelatinous. But this structure is precisely what allows it to survive. Instead of resisting pressure, it conforms to it. Its tissues are supported by high concentrations of osmolytes such as trimethylamine N-oxide, which stabilize proteins under extreme compression. There are no rigid bones to fracture, no air-filled cavities to collapse. What seems biologically weak is in fact an optimized design, an organism shaped entirely by the physics of its environment. Amphipods are small, shrimp-like crustaceans that thrive even at the deepest points of the Mariana Trench. Despite their size, they possess remarkable biochemical adaptations that allow survival under extreme pressure. Their cell membranes are stabilized by unique lipid compositions, while specialized proteins prevent structural collapse. Some species have been observed consuming organic debris, including plastic particles that have reached these depths. This highlights both their ecological role as scavengers and the extent of human impact. Their presence demonstrates that survival in the Hadal zone depends not on size or strength, but on molecular-level resilience and efficiency. Xenophyophores are single-celled organisms that inhabit the seafloor of deep ocean trenches, yet they can reach sizes of up to 10 centimeters, making them among the largest known unicellular life forms. They construct intricate structures from surrounding sediment, forming complex habitats on an otherwise barren seabed. Despite their simplicity, they play a significant ecological role by providing shelter for smaller organisms. Their existence challenges conventional assumptions about biological complexity, demonstrating that even at extreme depths, life can organize itself in unexpected and highly functional ways. Most of what is known about Hadal life comes from remotely operated vehicles, or ROVs, descending for hours into complete darkness before briefly illuminating the seafloor. The footage they capture is often unstable, with suspended sediment scattering light and distorting shapes. Within these constraints, unidentified organisms occasionally appear, elongated forms, slow-moving silhouettes, or structures that do not match known classifications. However, interpretation remains limited. Resolution, angle, and environmental interference can significantly alter perception. What appears unfamiliar or even unsettling is not necessarily unknown life, but often a product of incomplete observation under extreme conditions. Encounters with the bigfin squid in deep-sea ROV footage are exceptionally rare, and each observation raises more questions than answers. Its long, filament-like arms often extend far below the body, held in a rigid, angled posture that appears almost mechanical. Unlike active predators, it frequently remains nearly motionless, suspended in the water column. This behavior is not yet fully understood. It may be a passive feeding strategy, allowing the squid to intercept small particles or organisms drifting by. However, limited data and brief visual records make definitive conclusions difficult, leaving its true ecological role uncertain. In several deep-sea expeditions, operators have reported observing large, undefined shadows moving just beyond the effective range of artificial light. These forms lack clear boundaries and often disappear as the camera angle shifts or sediment is disturbed. Such observations are difficult to verify due to limited visibility, low resolution, and the scattering of light in dense particulate water. In many cases, what appears as a solid moving entity may result from overlapping shadows, drifting debris, or optical distortion. Under these conditions, perception becomes unreliable, and the distinction between a biological organism and a visual artifact is not always clear. Under extreme deep-sea conditions, visual interpretation is inherently unreliable. Light from ROVs travels through dense water filled with suspended particles, causing scattering and reducing clarity. This produces shifting shadows, distorted edges, and false motion cues. In addition, the lack of fixed reference points in total darkness makes it difficult for both cameras and human observers to accurately judge scale and distance. Slow-moving organisms such as gelatinous fish or drifting debris can appear larger or more structured than they actually are. What is perceived as a distinct entity is often the result of optical interference rather than the presence of an unknown organism. The blobfish is often cited as one of the most unusual marine animals, but its distorted appearance is largely a consequence of decompression. At its natural depth, typically between 600 and 1,200 meters, its body maintains a stable form under high pressure. Its tissues are gelatinous and slightly less dense than water, allowing it to hover above the seafloor with minimal energy expenditure. When brought to the surface, the drastic drop in pressure causes its structure to collapse, giving it the familiar melted appearance. What seems abnormal is not its true form, but the result of removing it from its native physical environment. Human perception is not a neutral process. It is shaped by evolutionary mechanisms designed to prioritize survival. In low information environments, such as deep ocean darkness, the brain tends to fill gaps with assumed patterns. This includes detecting shapes, movement, or intent where none may exist. Known as pattern recognition bias, this response increases sensitivity to potential threats, but also leads to false interpretations. Combined with isolation and unfamiliar stimuli, this can amplify fear responses. What is perceived as something watching, following, or lurking is often the brain projecting structure onto randomness rather than detecting an actual presence. In 1963, during a deep-sea survey in Suruga Bay, Japan, fishermen reported repeated encounters with an unusually large, shadow-like organism moving slowly beneath their vessels at depths estimated between 300 and 500 meters. The sightings were consistent over several weeks, particularly at night, when the water surface showed unexplained disturbances and occasional bioluminescent flashes. One crew documented a long, pale appendage, briefly breaking the surface before submerging again. The object was described as exceeding 15 meters in length, with no clearly defined head or tail. Local records connected these observations to earlier accounts from the same region in 1933, where similar shapes had been reported by coastal crews. The phenomenon was referred to informally as a deep-water giant, though no physical specimen was ever recovered. Naval authorities logged the reports but classified them as unverified due to the lack of direct evidence. Despite multiple recorded encounters, the origin and nature of the observed entity remained unresolved, and no confirmed identification was ever established. The Mariana Trench exists at a depth where direct human observation is nearly impossible, and most biological data comes from brief, instrument-limited encounters. Unlike coastal regions or mid-depth zones, there are no consistent, repeated visual records of large, unidentified organisms in this environment. All confirmed species, from gelatinous snailfish to small crustaceans, share a common pattern of structural simplicity and pressure adaptation. While isolated reports and interpretations exist in other parts of the ocean, the Hadal Zone itself shows no verified evidence of large, complex, unknown life. What remains uncertain is not the presence of hidden giants, but the extent of undiscovered micro-ecosystems adapted to extreme conditions.